Hello everyone, my name is Susana Iglesias and I am the Research Associate developing the project titled Application of Recycled Carbon Black in Printable Electronic and Photovoltaic Devices, which has been awarded funding by the UK Circular Economy Hub. This project is led by Professor Elizabeth Gibson, head of the Energy Materials Laboratory in Newcastle University, of which I am part as an RA, and counts on the invaluable support of our partners Wastefront, an Oslo-founded rubber waste recycling company, and the Royal Air Force Leeming Base. So, to briefly give you a bit of context, we know that approximately 29 million metric tons of vehicle tires reach the end of their lifespan each year. And of them, around 10% would end up in landfill, risking the pollution of water systems. Most of them will be incinerated, although with a poor energy recovery of around 33%. And about 22 kilograms of CO2 will be expected to be released for each tire. And although some of these tires will be recycled, most of them, or largely, they will be recycled in the form of shredded materials for sport pitches and playgrounds, which also raises some concerns over pollution, similarly to the deposition in a landfill. Our partners Wastefront have planned a new plant at Sunderland, northeast of the UK, which will process around 80,000 tons of tires from trucks and cars per year. And following their proprietary processes that minimizes waste, CO2, water and heat, they're able to generate two main products, liquid fuels, which they already have customers in place, and carbon black, for which we seek to identify opportunities as a higher value product in electronic and electrochemical devices, and for which we're raising the question, can we use recycled carbon black in printable photovoltaics? Now, raising this question is necessary if we have a look at the current context of traditional photovoltaics. So currently, we potentially have 800 terawatts of power available globally from the sunlight if we were to use traditional photovoltaics, so our current technology, which is predominantly silicon. So that is plenty to fulfill our 2050 target, which stems around 4% of that number, with net zero greenhouse gas emissions. However, reaching these objectives has two caveats. The first one being that about 70 million tons of PV waste is expected to be generated by 2050, as calculated by ARENA, and the challenges in the supply chains of critical materials for renewable energy and electronics already exist, as we have probably seen over the past couple of months. So that's where emerging solar technologies or third generation photovoltaics come in. They can be processed very easily at a very low cost. They're fully recyclable, and they have the potential to be used both indoors, for example, powering sensors and other IoT devices instead of using batteries, as well as the traditional power generation that we would expect to have from PV outdoors. Therefore, using recycled materials in these devices could lead to further savings in embedded energy and reduced environmental impact. For our motivation and novelty, we'll present the triple mesoscopic stack, which is one of the architectures employed in third generation photovoltaics, and we aim at changing the counter electrode of the device, which is often made by a carbon ink using a certain percentage of carbon black amongst other elements. So we propose the use of recovered carbon black with the unique added value of outdoor testing, providing real-time data to our partner in the MOD. That is, the MOD, we know it owns around 1.4% of the land in the UK and contributes to 50% of the UK central government emissions, and also has very ambitious decarbonisation targets, which is to become net zero by 2050. So we will be testing our devices at IRF Leeming, as I said before, in the UK, and that will enable us to provide data to decision makers in the MOD to demonstrate the potential for using materials recycled in the UK for power generated in the UK that could support and accelerate the UK transition to clean, affordable and secure energy. So we can divide our aims and objectives in three main blocks in this project. The first one would be fabricating and testing the devices. The second one would be assessing the circularity of such devices. And the last one will be directly linked to the impact of such fabrication and discovery. So for the fabrication and testing, we will first be preparing carbon pastes using material recovered from the recycled tires. Test its electronic and electrochemical properties compared to virgin carbon black or other commercial carbon inks used in photovoltaics, and apply the material in printable solar cells, evaluating their performance under both simulated and real sunlight conditions outdoors at RAF Leeming. Now, to assess the circularity, we will prove and demonstrate the recycling of all the materials contained in such solar cells and evaluate the potential carbon savings and environmental impact through LCA. Finally, we will provide data on the performance and potential market opportunity to waste front for a business case for further investment, disseminate and discuss the outcomes with policymakers at DEFRA, BEIS, and the MOD, and showcase the work and learning in publications and at a circular economy events. Regarding our project plan and work packages, we have divided the workload in 4 main packages. So package number 1 will be including the characterization of carbon black materials in films. So that is characterizing using lab techniques, the carbon black composition, with using, for example, XRD, TGA, XPS, Raman. The preparation of the carbon paste and the thin film deposition, primarily by screen printing, but also opening to other methods like spray coating or slow dye coating. And lastly, the film characterization, so characterizing the most important properties for the current application in photovoltaics, which would be the conductivity, which will tell us how fast or how many electrons or charge we can extract from the material, and the porosity, which will tell us how much active material we're able to percolate through the device, which in turn will mean that we'll have more electricity generated. The second work package starts from the 5th month onwards, but approximately until the 9th month. And that is to do with the fabrication and optimization of these triple mesoscopic stacks using either perovskites or dyes as the absorbing material, potentially both, then followed by encapsulation and both indoor and outdoor testing. So for the outdoor testing, we have also included another sub-objective of subsection, which is the assembly of a testing rig that would enable us to obtain data remotely from RAF Leeming into Newcastle University. The third work package includes recycling of the materials, so of the solar cells. So we have to prove that the disassembly of the materials is possible by removing mechanically the encapsulants and dissolving the photoabsorbent with some solvents. And then the reassembly, so that is the thermal treatment of the stack that we've printed originally, and the recycling of the photoabsorber, so the recrystallization, so that we can introduce it back into that stack and then reuse again that solar cell. Finally, work package 4, which has to do with impact and opportunities, and that will include at the end of the 9th to 11th month, including the 12th month as well, the adaptation of a financial model, LCA, and exploration of potential IP for waste from, and a report writing and dissemination of such information, both in publication as well as in circular economy events. Regarding our updates and the current research that we're carrying out up to the 6-month milestone, we have completed work package 1 and pretty much most of work package 2. So that is, we've characterized the material, created different compositions of carbon pastes, selected the best compositions to transform into films, and then characterize via 4-point probe conductivity, some BET absorption measurements, as well as some SEM, which is the images of scanning electron microscopy that you can see in this image, so that we can see the size of the pores, and some XPS, which will help us assess the electronic characteristics of the interfaces between different layers. of the solar cell. We have fabricated preliminary solar devices, which are showcased here on the right. And for a first test, we've been surprisingly pleased by observing that indeed the recycled camber black is a quite promising material as a carbon ink in a triple mesoscopic stack, since it gives quite high open circuit voltages compared to non-optimized virgin carbon black or commercial Elcocar paste. And that can also be seen in the IV scans. Finally, we have also assembled 2 testing rigs, and we could start testing the devices outdoors since its installation date from the 18th of April 2023 onwards. The upcoming work is regarding the second package with the outdoor testing at RAF Leeming. At the moment, we have ready 2 types of testing rigs, one that is steady and is going to be left in the field, and that is able to obtain data from sunlight intensity, solar cell temperature, ambient temperature and humidity, and of course, solar cell power. And also we have developed a portable tester that can be strapped to the arm of any user and assess the power output of the solar cells on the go. Finally, for the next following 6 months, we will also be working at the recycling and with the disassembly and reassembly of the solar cell components, and also study the impact of opportunities using the LCA, IP exploration, as well as report writing and dissemination. Thank you very much for your attention. If you're interested in the project, please contact us and visit our webpage at newcastle.ac.uk.